Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and today I am psyched. And I'm psyched because I am going to loosen my hug on Hubble just a little bit today, and I'm going to be giving some love to its successor, the James Webb Space Telescope. And today we're going to be giving some love to that because we've got an important milestone that was reached today because NASA announced, drum roll please. Oh, thank you for doing that. The 18th and final mirror segment has been installed on the primary mirror plane for the James Webb Space Telescope, and we're going to talk about what that was like, what that process was like, and with the people who are involved both in overseeing the James Webb Space Telescope as well as those actually building it. And I'll introduce my guests here in just a minute, but before I start, let me welcome my friends, co-hosts, and colleagues, Dr. Carol Christian. She's the Hubble Space Telescope Outreach Scientist. Hi, Carol. It's good to see you again.
Hello, Tony. Good to see you, too.
Yes, I hope so. And also with me is Scott Lewis. He is the Internet driver extraordinaire. He keeps track of all of the social media stuff during the Hangout. Hi, Scott. It's good to see you again.
Good to see you, too, Tony. How's it going?
I'm doing great. Like I said, I am psyched. And cannot wait. Cannot wait to talk about
you're
today's
cheating
stuff.
on the Hubble huggers. So
I know. He's listening as a group.
You know, Hubble is great to hug. JWST is a little bit pokey. I don't know if I could hug it as nicely. It's also really big, so I don't know if it's
it is really
easy
big
to hug. It's got a lot of little pokey sides on it. I'm not sure it's
But
pokey.
speaking of, I might have a picture later on of you and me hugging.
Yes, I saw it on Twitter.
No,
Thank you for
no,
that.
that's okay.
It's related to JWST, too, so it's even better. It all ties in.
You know what I should do next time I'm at the Institute is I should go to the lobby and actually try and hug that big scale model. That's what I should do. Okay, so we're going to get started, I have an anecdote that I want to share with you today. My anecdote is about Clyde Tombaugh because today marks his 110th birthday. And my anecdote is, I actually met him. I got a chance to meet Clyde Tombaugh. He is the discoverer of the minor planet Pluto, but at the time he discovered it, it was
dwarf planet.
Dwarf planet, okay. Yeah, well, words are important, so I should get it right. Dwarf planet Pluto. And I met him at, you may not know this, but my very first, well, I know you don't know because I'm telling you for the first time. My very first job right out of high school was working at a place in Alamogordo, New Mexico called the Clyde Tombaugh Space
I already heard this
Theater.
story. I already heard this story.
You have, but not everybody else.
Well, that's all that matters, Tony. Carol.
So Carol's heard it. Anyway, I met him. He was a wonderful man. He was very kind, very generous, and he was very inspiring to talk to because he was, telling us all kinds of stories about his telescopes because he observed, I think he lived in Las Cruces, and he told us all about the telescopes that he used. So in honor of him and his 110th birthday, I just wanted to give him a shout out because he's an awesome person and very inspiring.
Yeah, really.
So that is my anecdote. Okay, let's get to the Hangout today. But before we start, we need your interaction, folks. We need you guys to get involved. And that means we want your comments and your questions. And to tell you how you can do that is Scott Lewis.
So we've changed things up. We're following how we were last week, and last week was wonderful. So we're going to keep that going on here. And I'm already seeing a bunch of guys in there. So since we're streaming live on YouTube, we've enabled the YouTube live chat to where you can chat with each other. You can ask us questions and make comments. And as it's going on, I'll be perusing through there and directing any questions that are going on in your chat onto the show. So please keep on doing that. Also, while we're going through, we'll be live tweeting from at Hubble Telescope, and we'll be using the hashtag Hubble Hangout, even though this is JWST related. So I'll be looking at everything over there on Twitter. So please feel free to ask us any questions, make any comments there that you feel is really important to what's going on here, and we'll try to get them up live on the show.
Awesome, great. So we hope you guys will have some great comments and questions for our guests today, because with me today are two people involved very heavily in the JWST mission. With me is Dr. Mark. He is now the director of the astrophysics division at the Goddard Space Flight Center. He used to be the observatory project scientist for JWST. Welcome, Mark. It's glad to have you back in our Hangouts.
I'm pleased to be back, Tony. Thank you for having me.
Cool, great. And also with me is Dr. Gary Matthews. He has the coolest job in the universe. It's one I want when he decides to move on. He is the Director of Universe Exploration. That's a job.
Right. That's a good title.
What?
It's a great title.
I can imagine. Boy, that's my old job, actually. I hope you can keep up with that. So.
Well, since I own my own business, I think I'm going to change my title to something similar to that and just go with it.
Right.
New business in order.
So, for those of you who don't know, Harris Corporation is a subcontractor for Northrop Grumman, and they were the ones responsible for getting the mirrors assembled today, and we're going to talk to them about what was involved in that. But before I ask you my first question, Scott, can you put up that picture of what people who work at Goddard see when they come to work? This is what they see now at the Goddard Space Flight Center when they go to work. Dun, dun, dun.
Well, you could have told me that was the first one.
I should have told you to cue it up.
That would have been nice.
I should have queued it up. So he's getting it together right now.
Yeah, just a second. Let me get it.
And then while he's getting that up, I should also, another question that I would like to ask you guys is, well, hang on, wait, there it is. This is what people that go to work at Goddard see right now. Congrats, JWST team on successful completion of the primary mirror assembly. Now, my problem with this photo, and this is a question for both of you, is where's all the snow?
Snow is melted.
The snow is gone already.
Yeah.
Okay.
Rained yesterday.
Were you guys in the building when everybody was doing all of that Snowmageddon or Snowzilla testing? They were staying in the building, I think, during all of that snow. Were you guys a part of that, Gary?
Well, we had people working during that, not over the weekend, but earlier in that following week, we had people slugging away, putting mirrors in. So, yep, we were there.
Yeah. So everybody was working during the snowstorm. Everybody is very dedicated, and rightfully so, to getting this telescope going. So, all right. So to set this up, I have to read this from this is just so well written. I'm going to read it directly from the press release. The 18th and final primary mirror segment is installed on what will be the biggest and most powerful space telescope ever launched. The final mirror installation Wednesday at NASA's Goddard Space Flight Center in Greenbelt, Maryland, marks an important milestone in the assembly of the agency's James Webb Space Telescope. So this is it. You guys have done it. You guys have put together the all 18 of the mirror segments, and while Scott's putting up a picture of what that looks like, let me ask you, Mark, what's the energy like there at Goddard right now? Is everybody excited?
Everybody's absolutely. I mean, I think the way you understand how excited people are is the number of people you see trailing past that window every day. So I go there every day and have been doing that for the last 6 months almost, just to see what's going on.
What you're talking about is there's this room at Goddard where it's kind of a balcony overlooking this very room here.
Exactly. It's the what we call the Building 29 window, where you can look in and see what's going on in the clean room. And
yes, I've been there several times. A
colossal number of people go there every day just to see what's happening and figure out which mirror was on and how many more we had to go. So yeah, there's a lot of energy. People are really sort of buzzed about this. And
so
we finished it.
I know, and so when a big milestone like this is imminent, do you get a lot more people pressing their noses up against that window?
We get the complete range. Everybody wants to come and see it. People are having conferences in Washington. They want to come out and view it. So, we have all the committees having meetings here so they can come and see what's going on. So it's very, very popular.
Now this thing is really big, and it's really hard to get a sense of how big it is in pictures, but here in the one that Scott's got up, you can kind of see in the background there's 3 guys sort of standing around and looking down while robot arms do some work on it. It gives you kind of a sense of just how big this thing is. So Gary, let me ask you, so you are you work for the Harris Corporation, which is a subcontractor for the Northrop Grumman company, which is the main, I think, assembly company.
They're the prime. Yep.
So describe a little bit about what your company's doing and what your role is here.
Well, if you go back to that previous picture, we're really responsible for the equipment to build the telescope. So we've all the equipment you see there to install the mirrors, was built by Harris, and then we're responsible for installing those and making sure they're in the right place. So you know, it's been a great experience to be part of something like this, and the team is extremely dedicated. They work 2 shifts, 20 hours a day, and they've made this happen in an unbelievable amount of time.
So describe what this arm? I mean, what we're looking at here is what looks like one of the mirror segments being lowered down onto the plane. Is that correct?
Yeah, this is this is number 18, looking across the primary mirror. And you mentioned scale a few minutes ago. So remember, Hubble is about the size of 3 of those segments.
The primary mirror on Hubble.
Yeah, so the primary mirror in Hubble, in round numbers, about the size of just 3 of those, and we've got 18. So that's kind of how I think about scale. But this robotic arm, it's called the PAIF, the Primary Alignment Integration Fixture.
You guys could have done better than that, I think. PAIF? Okay.
Well, we have a SAFE also. It's the secondary integration.
Oh, SAFE and PAIF. Okay.
It's NASA, Tony.
Okay.
In the wee hours in the morning, it made sense.
Yeah, you know what?
It's sounded good before. Anyway, so the PAIF is quite a piece of equipment. You can see it's attached to this big gantry system. It's got, I think, 8 or 9 degrees of freedom. Normally, I think 6. But that whole lower assembly swivels in a circle. It swivels out, mainly because the primary mirror is curved, right? You're looking at a big bowl there.
That's right.
And then it moves directly up and down, and then you can see the really fine stage, the hexapod there. You see the 6 black legs there. The reference is in the middle, that Y-shaped fixture in the middle. That is the reference that we built the telescope off of. It's got some SMR, spherically mounted retroreflectors that these laser trackers can see. And just beside the PAIF, you can see that on that gray stand, there's it's kind of white with a black top. Yeah, so that's a laser. Yeah, in the back. Yeah, so there's between 3 and 4 of those, and we use them together. They're linked together via some special software we use. Allows us to beat down the errors of any one. So we bring the mirror in. Excuse me. We set it down to not quite touching, and we get it into alignment. And there's a whole bunch of metrology that has to happen to make sure it's in the right place.
What's metrology?
Metrology is some very precise optical alignments. So it's just a general term we use for precision measurements.
Okay, I want to get to that in just a minute as far as how these things are figured and oriented. But over the top of all of these things, I can see these. They look like handles on there.
Yeah.
Now,
so
what is that?
Well, so they're my fault. Originally,
Nice. Thanks, Gary.
And we have ruined the aesthetic pleasure of the primary mirror here. So when we were first contemplating putting this together, we were never going to cover the mirrors. They were just going to be gold coated just beautiful. As time went on, and the theory was, nobody's ever going to work over top of the primary mirror. So it's beautiful.
Really, people thought that was a good idea, just to leave it open.
That's terrifying.
In theory, it was a great idea at the time, but so as things got closer and reality became clear, it was like, oh, wait a minute. So we designed these very light covers. They actually attach. They actually rest on the mirror physically, right on the corners, and those are handles to get them off. And so those are very light composite covers, and we have a little fixture that'll come and grab those handles and gently lift them off when we're all done. So the aesthetic pleasure, I mean, I dream of having that 6.5 meter primary mirror exposed, but we all feel a lot better with the covers on there.
Yeah, I bet. Mark, how about you, Mark? What do you think? Was that
Well,
Get there with
from
their-
my perspective is that this is, you know, as you said, I used to be a project scientist, and this is project science at work, because, you know, the need for the covers is to prevent fallout or dust particles getting on the mirrors, and dust particles scatter light, which then impacts the sensitivity of the science that we'll be able to do. So, you know, the project science team and myself in particular have been advocating for these mirrors to be covered as much as possible, all the way up to the very last minute, so that we minimize the amount of stuff that we get on the mirrors, because we have extremely tight specifications.
I suppose an argument
I just
again.
want to put out one principle. I didn't work on JWST, but I have worked on a number of telescopes, and every time somebody in a meeting said never, I said, don't say never, because it'll happen. So
Yeah, I could just see me,
that's
especially.
my guiding principle.
Right. Our
Walking the room.
principle is that we only uncover them when the mirrors are vertical,
Yeah.
so they're not going to pick up
Yeah.
so much fallout.
Now, that clean room is pretty impressive. I mean, I'm sure you've got particle and dust and debris, all that kind of stuff, kept to an absolute minimum, maybe even a perfect one. I don't know, but there's got to be. I know the clean room standards are pretty high, but yeah, there's a HEPA filter wall just along the whole side of it to keep the particles out.
And the containers for the mirrors are like magnificent on their own. I mean, they're these beautiful bell jars, and they're just like fantastic. I was totally fascinated by them.
Yeah,
they're really cool.
Yeah, little moving clean rooms. Yeah.
Was that what they? Yeah, they're pretty impressive.
They're very cool.
I look at it and I think, boy, that seems a little over-engineered, and then I realize, well, wait a minute, these are the primary mirrors we're talking about. To be messing that up. So, so getting back to the picture that was up, and you don't have to put it up against Scott, but I just want to go back to what you were holding it up with this kind of arm thing. How was that being affixed to the mirror segment? What it looked like, almost like it was suction, but it wasn't that, was it? You had it somehow.
No, there's an arm. Yeah, there's an arm. You can't see it in that picture, but there's an arm that goes around the back of the mirror, and that holds it while we install it. And then when we're done, that arm has to come out in relatively small pieces. So we actually take that part of the PAFE apart to get it out of there once we're done integrating the mirror onto the backplane. So a lot of thought and engineering went into exactly how we were going to, mount those mirrors and how all the pieces were going to fit together and come out at the end.
Okay, I'm going to ask you this next question. I want you to think hard about it now. Be honest, Gary. Were you nervous about dropping one of these things?
About dropping one? No.
Yeah. You weren't nervous at all?
Nope. No, we've got we handle lots of mirrors, and nobody really carries these around. There's fixtures for every operation, and so it's not like you get a couple folks and they carry them from one place to the other. Everything has a handling fixture, and it's very, very controlled, and that's what this team does every day. When they're not here, they're doing the same thing up in Rochester. So.
Okay. Yeah, that's true. And there's also a lot of testing of even those fixtures that go before they even use those. So there's a lot of testing that goes on with that as well. Okay, well,
Tony, there was somebody just flashed up a question saying, "Are we going to test?"
Yeah, I was going to get to that. Go ahead. Let me just read it out real quick. Elad Everon from at YouTube. They are going to test it before putting it in orbit, right?
And the answer is yes, indeed we are. And not only are we going to test it, but we're going to test it at the temperature that it will operate at, which is 40 degrees above absolute zero. So we will send it to Texas. It will get put in a massive chamber that they have at the Johnson Space Center, and we will do an end-to-end optical test at the operating temperature.
Now, even though this can be folded, you're not going to fold it for the testing. You mean, I guess I was thinking you guys have chambers in Goddard that you could do something with, but I guess are they too small? You have to ship it all the way to Texas?
The chambers are actually too small, yes. So, and to be honest with you, we're actually using them for other things on JWST. So right now, we're just finishing up the cryo test of the ISIM, the Integrated Science Instrument Module, which is basically the 4 science instruments. And that test began at the end of October, and it's in the final stages of warming back room temperature right now, and that will conclude all of the optical testing of the science instruments.
Right. So that's going, as you point out, going on at Goddard. Scott, in his magic, has put up a picture of those shipping containers Carol was talking about. Those are like miniature vacuum thermos bottles, right?
And this is actually from our behind-the-scenes director from her recent visit. So this is from Elena. She just emailed it to me from her visit at Goddard. So thank you,
we
Elena.
went down there. Yeah, we went and saw that. They're very cool. And there was actually one that didn't have a mirror in it that was sitting out outside this room. So we got to actually see one up close and personal.
Is it one segment per container, or are you stacking them up in there, or how many?
No, just one per container, and they're purged with nitrogen, dry nitrogen. To keep them clean. They sat in there, Mark, what, for 2 years?
Yeah, pretty much.
Wow. Wow, talk about being put on ice for 2 years. Wow.
So getting back to the covers for a minute, is there any? I suppose an argument against the covers being on there might be that the covers themselves could actually do some damage. I suppose that's the risk of that happening is a lot less than maybe damage from some kind of dust particles, correct?
Yeah, it's really balancing the risk. You put the covers on, and risk when you put the covers on or you take them off, you damage the mirror, versus what can happen if it's uncovered. And it's we work that closely with the NASA program and balance that risk and try to do the right thing here.
Well, I'll try to remember when I'm on my tour and I've got my ice cream cone. I won't dump it on the top of it. I promise I'll be careful. So, okay, well, let me ask you about the weight of these things. So you got a mirror segment going down onto the back plane. How much do one of those mirror segments weigh, Mark?
I'm going to pass that to Gary.
Oh, okay. I got you. Put you on the spot. Sorry about that.
They're about 80 pounds.
80 pounds. 80 pounds for one.
Yes.
Now that's still pretty light though, because how big is one segment?
1.3 meters.
1.3 meters. And what are these things made of? They're made of some kind of special space age stuff, right?
Well, they're made out of beryllium.
Right.
So beryllium is an outstanding material for cryogenics. It has a 0 CTE starting at about 100 Kelvin. And from 100 Kelvin down to absolute zero, they don't change their shape. So it's a 0 CTE material, just perfect for cryo applications.
CTE, what's that?
A coefficient of thermal expansion.
Ah, okay.
So when the temperature changes, nothing happens to them.
Meaning they don't flex much and they don't float much at cold temperature, as temperatures change, correct?
Right, they're very stable. Mark can go into this, but we're only going to adjust the system about once a month. So it has to all stay put. Even though the temperatures will vary a few degrees Kelvin over a month, the shape can't change. So using a 0 CT material like this is very advantageous.
Okay, I want to dive into this just a little bit more because for those of you who don't understand how telescopes work, most telescope primaries have a shape on them that's parabolic, and they focus that to a point. And because this telescope is so large, and because it has to be folded up and fit inside of a rocket body, these things are built in these segments like they are for a lot of other reasons. And so I imagine, Gary, that each segment has got to be put on in the right orientation, right? If you rotated one of them by a little bit, you're going to mess up the whole thing, right?
That would not be a good day in
the
life of the telescope.
I'm sorry?
Well, shiny side up.
Right, good.
Shiny side up is good.
Rule one. Do you guys have T-shirts that say that?
But they are parabola, and there's actually a mark on each mirror that tells you what the orientation is. So we're always very careful to get that orientation marked the way it is referenced on the drawing.
So really advanced IKEA instructions on how to put this thing together.
Yeah, it's a manual more than a pamphlet.
The figure of this mirror is pretty important, and so each one is done separately. I think it was built by the Ball Aerospace Corporation, Boulder, correct? They're the ones who made the mirror segments.
That is correct. Yep.
Okay, so and they're coated with a very light and thin layer of gold, actual gold, because that's that's highly reflective in the infrared.
That's right.
Okay. So, but it's not. I think, Mark, I don't know if you remember, maybe one of you guys remember how much. It's like not very much gold at all. It's like a little tiny, very tiny amount, because it's like one atom thick or something on the surface, right?
It's slightly thicker than that, but it is a very thin layer. It's just enough so that we get something like 98% reflectivity from each of the mirrors. So you build a big telescope like this, you want to maximize its performance, and I think beryllium reflects about 70% in the infrared, whereas gold is 98. So we just put a little layer of gold on to make sure that we get the maximum reflectivity and efficiency from the mirror.
Okay, good. Well, I'm not sure which one of you is best able to comment on this, but in addition to the tilt of the backplane, you've got this sort of curve to the backplane itself. Each mirror segment can be articulated just a little bit, right, on its own.
Yeah, there's actually 7 actuators per mirror. So there's 6 rigid body actuators, so we can move it in tip, tilt, piston, and the 2 descenders. And then there's 1 radius of curvature actuator. There's actually some rods that connect each of the points of the hex to the middle, and you can push up and down on that middle actuator, and it changes the radius of curvature. So when you make this a single primary, we call it phasing. When the primary mirror is phased, you'll tip and tilt all the mirrors so that they're within a few nanometers of each other surface, and then adjust the radius of curvature so that they all work like one large 6.5 meter mirror.
Now, why do you need that, though? Once you mount it properly and it unfolds correctly, isn't that it? Do you need to have any further control after that point?
The deployments aren't perfect. There's hinges and they latch up.
Oh, okay. So that's to kind of correct for little tiny variations in the hinge openings and things.
Well, that and there's the backplane has instability. Everything has instability. So because we're segmented, just like the ground-based telescopes, you have to be able to move each of the mirrors. So Mark, you might be able to comment on that too.
And you also have to remember, Tony, that once we deploy everything, as Gary said, there are minor things there, but then it cools down to 40 Kelvin, so you've got a very large temperature change. So once you've deployed everything and it's cooled down, you may be very close to the shape you want, but you're never exactly there. And the other thing I should have mentioned, of course, is that during launch, this whole structure sees a lot of vibration and acoustic noise as a result of the actual launch experience. So it's unrealistic to expect that all the mirrors stay perfectly aligned when you unfold everything again. So the way we operate it is, once we've deployed everything and we've moved all the mirrors to the right place, we then do a 2-stage alignment of each of the segments. The first one called coarse, which gets the images in approximately the right place. And then we do a fine alignment, which actually, ironically, uses a lot of the techniques we developed when we were trying to understand spherical aberration on Hubble, a technique called phase retrieval, to do the fine alignment. And phase retrieval just means that you take images on either side of the focus point, and then you can analyze those defocused images to figure out the optimum movement for each mirror, so that you end up with essentially your best fit to the mirror shape. So we do that once every 2 weeks, and in the meantime, over those 2 weeks, we're doing science with the telescope, so it's moving slightly each time and seeing a very slightly different thermal environment, fractions of a degree. And slowly over 2 weeks, there's a very small drift of some of the segments away from their optimum alignment. So after 2 weeks, we go back and we just do a fine tune to make sure that everything's perfect again.
Okay, that was going to be my next question. So once you're out at L2 and you're out, 1.5 million kilometers away, the telescope has reached its operating temperature. You've done these adjustments over the course of 2 weeks. This isn't something you expect to do very often after that, correct?
Well, it takes us almost a month to do the initial alignment after launch. And then once it's aligned, we go back and tweak it every 2 weeks. So we do what we call a fine-tuning every 2 weeks, just to keep everything absolutely perfect.
And then they're not done. Then they've done the mirror, and then there are science instruments, and that isn't instant. So you might talk about that, Mark.
I think you're going to have the world's attention during this point. I mean,
all the time, yes.
The whole sort of commissioning phase of JWST has no instant gratification. You know, it's a very sequential process that has a lot of steps to go from this, you know, folded up telescope to a fully deployed telescope that's reached the right temperature, that has the mirrors properly adjusted and all the instruments set up to start doing science. So there'll be a lot of interesting images as we go. When you first deploy the telescope, you're going to see 18 individual images all in different states of focus until we fine-tune the mirrors. So then once we get that, we have to stack them up into one image. And then, as I said, we do the phase retrieval to get the fine-tuning.
boy,
Carol said you then have to tweak the focus on the instrument. So there's a lot of steps to get to doing science.
there's going to be a lot of Rolaids being sold during this part during this time. I can see that already. I myself will be stocking up, watching for every bit of news that comes out of this. This is going to be amazing. This whole process, going from launch to deployment, is going to take how long more? The entire process. What are you giving it as far as the timeline?
The whole commissioning period is 6 months, and probably it's the first 4 months to actually get to the point where we can take focused images.
Okay, I'm going to bring in a question here from YouTube on from Sprojo. He's saying, I know it, and this is related to what we were just talking about. He goes, I know it is still in assembly stages, but I'm very interested in the launch, it went away, and deployment process, and what concerns you have with it being such precious cargo. Thanks from New Zealand. So he's interested in the launch and deployment process, and we can talk briefly, just sort of, yeah, I know it's going to be a big deal, but if you can just give us an overview of what that's going to be like.
Well, I mean, basically, as soon as we launch, we have outgassing from the fairing. We get to the various stages of separation of the payload, and once the telescope is actually released from the fairing and is out there on its own, we immediately start doing the first deployments. So very quickly after we launch, we get the solar panel out because we need power. We also get out the communications, and these all happen in solar panels are out in very short time. About a day after that, we get our communications dish out. We also have to do our very first burn to get to the right orbit fairly quickly as well. And then once we've done those, we sort of take slightly more leisurely approach to then doing the deployments and unpacking the telescope element by element. So
yeah, let me just point out while you're talking about that there is a really detailed video of this on NASA Webb Telescope's YouTube channel that you can watch. It's just called Webb Deployment, or maybe it's called JWST Deployment. I don't know what they named it, but it was made by Northrop Grumman, and it goes through in very clear detail every single step, and it even has a little timeline at the bottom of where it's going to be in its process on its way to L2, where it's going to be. Every little step is going to be done, and it's labeled very well. So that, if you haven't seen it yet, you have to check it out, because there's not a better resource, I think, that gives you an idea of what's going to happen. So.
Right. So I think that's a really good resource to go look at. But in very simple terms, once we've done the first burn to get to the right orbit, the big things that we do are unpacking the sun shield and then deploying the 5-layer sun shield, and then we start deploying the primary mirror. So we start by unfurling the secondary mirror, and that's followed by the 2 wings of the primary mirror, which you can see in the images that we've been looking at today. At the moment, they're actually deployed into the final configuration, but 3 mirrors on each side actually fold back around the payload during launch. So then we get the mirrors out, and then it's kind of a long wait while we wait for the instruments to reach their operating temperatures. And once the instruments are cold enough and the sensors are cold enough, we can start taking images to get the mirror aligned.
Yes, and I do see your comments on YouTube, and I'm going to get to most of them in just a minute. I just want, or all of them in just a second, but I want to ask Gary something real quick. So today was a big day. You've got the 18th mirror segment out, a big milestone in the mission, and it was the responsibility of the Harris Corporation to get that done. What's next for you guys? What else are you guys responsible for on the mission?
Well, it's no time to rest yet. We have a couple more things to do on the telescope itself. The aft optics assembly needs to go in. That's the tertiary, and there's a fine steering mirror that go in, and then the secondary mirror has to go in.
Are you guys installing the secondary as well?
Yes. Yep.
Okay, so the boom and the whole thing that comes out.
Yeah, so the boom will come back down. It's we call it over deployed right now. If you look at that picture, it's actually leaning up against the wall. Can you bring maybe the high? I think it's called high view or something.
Oh yeah, and the one that Scott was showing before.
Yeah.
Further away, yeah.
Yeah. So if you look at that picture, that secondary mirror, there's actually 3 struts. We disconnected one.
Mm-hmm.
Those are the fixed struts, where they're actually hanging on the wall.
Look how far that sticks up. Look at those men on the right there, and look how far that thing goes up. That's huge.
It's way up there.
So we will. So when the aft optics assembly is on, we'll walk this. We call it walking it down, and put it back in its stowed configuration and put the secondary on. And then we're not done yet. That's just a telescope build. We'll help NASA put the instrument in, the ISIM. There's a whole bunch of thermal hardware that has to go on. So there's a lot to do through the rest of this year, and then we all head down to Johnson and do some cryo testing.
So how do you pack it to send it?
It'll fold up, and it goes.
Lots of bubble wrap.
Lots. Yeah, it goes into stars. I didn't send a picture of stars. But it's a very large shipping container that goes into a C5, and we'll fly it from Maryland down to Houston.
Great.
Did Ball Aerospace make the secondary also?
Yes, they did.
Now, is it like a Schmidt-Cassegrain where you've got this? Well, no, because that would be a spherical mirror for primary, where it goes up to the secondary, and then the secondary mirror is also a spherical curvature, and it goes back down. Do we know what kind of mirror is the secondary?
So this is called a TMA, a 3-mirror anastigmat. So
okay.
So the primary is almost a parabola, and the secondary is almost a hyperbola. And it actually works off axis, so the telescope's kind of looking out the side a little bit.
There's a lot of amateur astronomers getting this right now, so
yeah,
that's glad I brought it up.
And so the tertiary removes the astigmatism because it's kind of looking out the side.
I was going to ask about the tertiary. Okay.
Yeah, so the tertiary kind of corrects that, and it flattens the focal plane. So Hubble is a Ritchie-Accretion, which is a modified Cassegrain,
right?
Which is a perfect parabola and a perfect hyperbola. The Hubble focal plane is curved, so the tertiary will kind of flattens out. It's not perfectly flat, but the focal area is somewhat flat and very large compared to Hubble.
Yeah.
Okay, good. Well, that's good. Did you want to add something to that, Mark? You like you were about to say something?
No.
Okay, so let me get some of these comments then. Keith Durant from YouTube. Full deployment cannot be done under normal gravity, so no, they are not going to test it. It better work. That's just not true. When I talk to people, it is going to be tested with the fact that we're doing it in gravity corrected for, right, Mark?
Right. Well, the previous question that I answered was in respect to optical testing. That is putting light onto putting light through the whole optical system, and that we are going to do at temperature. The deployments are being tested in gravity, so it is true to say that we cannot do a zero gravity, as it were, deployment test, but all the individual pieces of the deployment are being tested independently, and once we assemble the whole telescope, there will be several deployment tests done at Northrop Grumman of the whole observatory. So everything will be tested on the ground in gravity.
Yeah. So if you orient the hinges properly with respect to gravity, they don't know they're in gravity. So you do
That's what I was hoping. Yes, because there is a way to do this where you can.
You do some offloading, and then the real motors can run. They don't know they're sitting in gravity. So it's carefully choreographed. You have to be very careful because you can also break things that aren't made to do things in gravity. But well rehearsed and choreographed to practice and verify the deployments.
Okay.
And that's one of the, I mean, all of the hardware to do the testing of this telescope is almost as important as the testing, because as Gary says, the hardware has to be able to do gravity offloading and also protect our payload while we do the tests.
Now, by hardware, you're meaning all those little tiny hinges and pins and...
Government calls it, NASA rather calls it ground system equipment, GSE. But some of the hardware that we're building just to test the telescope is, pretty interesting engineering in itself.
You have to build all this other stuff that manipulates everything, and that all has to be perfect too. As we well know in Hubble, testing equipment is important.
Yeah, right. And there's this thing called space qualified. Can one of you talk about that a little bit? Maybe Gary, can you talk a little bit about what it means to be space qualified?
So that's just an incredible amount of rigor. So there's everything is space qualified that we're using on the telescope, from epoxies to the metals to the coatings. Every aspect is checked, double checked, and qualified at whatever the operating temperature would be, whatever environments it has to see, so that we can ensure that the system will work properly once it gets on orbit.
Do you test these things, this hardware, to a point of failure, and just to understand how it's going to maybe perhaps fail, and then maybe build another one that you're actually going to use, or is there any of that kind of testing done?
So at some levels, yes. So the actuators that are used to move the mirrors, for example, those went through life tests. And
to see how many times you could actuate them before they failed? Yep.
And more than one. They picked X number off a quote assembly line. Nothing's on an assembly line here, but a representative number of a lot. Tested those to failure, and then on the actual parts, you'll burn those in to make sure they don't have any early failures, and you're convinced that they're going to work properly. So and even the epoxies, we will when you get a new lot of epoxy in, you will do some testing on that lot under specific parameters to make sure that the epoxy is going to stick and perform the way your the specification says. You can't take any chances with flight hardware like this.
Great. Okay. Well, so let's see. Get to another one with Andrew Planet. This is also, well, they're all from YouTube. Are all the segments of the segmented dish made to come together in a foolproof way so they fit in place and no other way? Now, you mentioned that there was a mark on the segments to tell you which way to orient them, but were they built that way? Were there's really only one way to do it?
Well, you can't make anything foolproof. They're just way too ingenious. We have to be very careful. You could certainly put this thing together wrong, but there's we call them MIs, manufacturing instructions, that are derived from the drawings, and everything was double checked to make sure that it was installed properly. So just a lot of rigor as you build the system, because you could easily put the wrong segment in the wrong place. It would fit. All the interfaces are the same, so you could put the wrong flavor of mirror in the wrong place. Absolutely. Okay. But we're not going to do that, and we're going to check it down at Johnson to make sure.
Sure.
Awesome, great. Well, Mark, I have a question for you. And I know that you used to be the observatory project scientist, and now you're moved on to the director at the astrophysics division. But can you tell me, how are things going with JWST as a whole? Are you satisfied with the mission's progress? Are things going swimmingly, or do you have any concerns or any comments on how things are going?
So I think things are going really well. As you see from today's discussion, the primary mirror is completed. Gary's guys are about to put on the aft optics bench and the secondary mirror. And later on in the year, they'll insert the ISIM, the science instruments, into the back of that structure. We're just finishing up the testing of the instruments right now. That's the last cryo test dedicated to instrument testing that they'll see. They'll get to cryo again when we go to Texas, but the primary role of the instruments for that test is to support the optical testing. So from my perspective, everything is going really well. The team is staying on schedule. We're getting things done as they need to get done. And it's actually interesting, during the snowstorm, I saw a couple of people interviewed on TV who are actually, I think, part of Gary's team or the Northrop Grumman team, who are out walking in the blizzard. And they actually mentioned they were working on JWST, helping to build the mirror, and the TV presenter said, yeah, but you don't launch till 2018, right? And the answer is, that's true, but if you work on this program, that date's coming up really
I
quick.
know, it's right there. It's
only 2018.
Oh my gosh.
Our team is just doing a great job staying on schedule and getting this stuff built, on the day they say they're going to get stuff done. And that's what it takes to, build and deliver this telescope.
No, I think that's a really good point for any sort of space mission, is that it's not just, hey, you know what, we should do this. Where can I buy the biggest telescope? And just, it needs to be designed. There's thousands upon thousands of people involved to creating it, everything going, the planning stages and funding, years, if not decades, to get things going.
But this must be a real boost, because I have to tell. So I work on Hubble, but I've been down to the window and pressed my nose against it, and I have a selfie next to the window. But I did, but it's so exciting. I mean, it's like, wow, it's really real now. It's like we have a mirror, and there must be just tremendous momentum in the project now too.
There is, and
really.
I was asked by a reporter the other day, so what do you think when you go look through the window? And I think I disappointed him, because instead of saying, I look at the telescope and go, wow, I said, well, I start thinking about the science I'm going to want to do at this telescope. And for the scientists, it's, it's real. You look through the window of a telescope and you start thinking, wow, I better start thinking about writing proposals.
Exactly. Yes, exactly.
So,
and that's the best part about being a scientist is grants. Awesome.
Well, it's getting observing time to do the objects you want to study, and when you sort of look through the window and you suddenly start thinking it's time to write proposals to study Fomalhaut or whatever target you're interested in, and the project's going well.
And the mission is looking at the early science, right? Like, what are we going to do? So
absolutely.
So that's really very exciting.
Yeah, this is a real testament to the dedication of the people involved in building JWST. But let me ask you, Mark, what else is in store for 2016 for the mission? What can we look forward to in the coming months?
Well, as I hope you've sort of heard today, most of what we're doing over the next 2 years is test. And for the rest of this year, once Gary's guys have finished, putting together the telescope structure, and we've installed the science instrument module in the back, it's more testing. We'll be giving basically bagging that whole structure, which is going to need a pretty big bag, and doing vibration testing and acoustics testing to simulate the conditions inside the fairing when we launch on our Ariane 5. And then that whole structure gets sent down to Texas to get set up and ready to start testing at the in the cryogenic chamber at Texas next year. After that, in the final sort of year, it then goes to Northrop Grumman, and they basically mate the telescope structure with the sun shield and the spacecraft bus. While we're working here at Goddard putting together the telescope, Northrop Grumman are real busy out in Redondo Beach right now putting together the spacecraft bus, which is the structure that holds all the electronic boxes, the rocket propulsion thrusters, the communications, solar panel, all the housekeeping stuff you need for a spacecraft. And they're also starting to build the sun shield structure that will mount on top of that bus. So there's a lot going on, and there's, as I said, a lot of testing to be done over the next couple of years.
I am sensing in my future a JWST road trip. I might be doing a groupie. I'll follow along on the truck as it goes from Texas all the way back across the country in my own little going, woo-hoo, JWST.
And I'll just head down to Redondo because that's real close to me here in LA. And so I'll work on things over here. You do everything in Texas. We'll meet up. Right. We'll just meet in the middle.
There's a special truck, by the way, for this thing, isn't there? It was like specially built to move this thing around.
Yes. Yeah, it's called STARS. I forget what it stands for, though.
Yeah, it's got this amazing, like, I don't know how many axles, but it was enormous when I saw it. Okay, I'm going to get a couple questions from YouTube here. Galaxia is asking, will the telescope be 40 degrees K or space? Isn't the correct temperature of space at L2 around 6 degrees? How come the telescope will be so warm? I'm surprised. I thought it would be 6 degrees. So this is going to be a little bit warmer than surrounding space, correct?
That's correct, and the answer is because if we wanted to get it even colder, we'd turn off all the electronics boxes in the spacecraft. But we don't want to do that.
The purpose, right?
Wouldn't be very helpful.
Very cold telescopes that's still sitting on a warm spacecraft bus, and we still have to protect it from the sun. So, a good thermal balance between space and the fact that we actually, are attached to a pretty hot object, which is running close to room temperature, is how we get to 40.
Right, and Bill Flanagan's asking a question, I think that's wanting us to compare it with some of the ground-based telescopes. He goes, if the James Webb telescope was set up on the Andes or in Hawaii, how would it function comparably to other scopes? Now, first of all, this is an infrared telescope,
Right.
and both the Andes and Hawaii, while they are good infrared locations, they are pretty limited by the water vapor and other things in the atmosphere. So
that's correct.
Right.
What about? Go ahead.
You also would have the problem that the atmosphere, is turbulent. So unless you applied adaptive optics, you wouldn't get the same image quality either.
Right.
Yeah.
So the sensitivity would be heavily compromised, as would the
Image quality.
Except having said that, they are building a 30-meter telescope on the ground. So, I mean, large telescopes are being done.
They are, but it won't go at the same regime as JWST.
Right, that's correct. And
I mean, beyond the
Those are
moon.
light buckets.
Why go to the Andes if you can go beyond the moon? Come on.
exactly.
This is awesome.
Okay, so let me ask a science question. I guess I'll do this one for Mark. Sam Paropi, I'm sorry if I messed that up. How much will the program help with the search and research of exoplanets? That's actually one of its primary mission goals, isn't it, Mark?
Right. So this is the area of research that I work in, and I have to say I told you I was looking through the window thinking about doing observations with the telescope.
I'm going to see that planet. I'm going to see that one.
JWST is going to be really good for doing what we call transit observations. These are observations where exoplanets cross in front of their parent star or behind, and we can actually make observations that allow us to get near-infrared or mid-infrared spectra of the planet's atmospheres. So we're going to be able to do an awful lot of what we call comparative exoplanetology, comparing the atmospheres and the properties of different kinds of exoplanets and getting pretty high precision spectra of the atmospheres of these planets for the first time, especially hot Jupiters, hot Neptunes, and probably all the way down to some super Earths as well. So you'll be able to be really exciting. I think we're going to rewrite the book on exoplanet atmospheres.
So you'll be able to observe in a very similar fashion to how Kepler was. You're talking about the transit method, but just going to have much higher resolution.
Right. Well, Kepler's a survey instrument. We'll be studying the optimum objects that are found by surveys. So we'll probably look at some Kepler objects, but probably the biggest feeder of targets to JWST will be the TESS mission, which is doing an all-sky survey looking for the brightest parent stars with exoplanets.
Okay, and I'm going to ask a question now from Ron Swith. This is something we get a lot with JWST. A lot of people are concerned about the fact that it's going to be at the L2 point. He's going, why can't you put some sort of thruster on it to bring it back for servicing from L2? It's just not designed to be serviced, and so what's the deal with that? I'll let you comment on that, Mark, if you want to.
Okay, so the first answer is it does have thrusters, because even at the L2 point, which we actually orbit, we need to do small burns about once a month just to stay in orbit around L2. And we also have to do burns to relieve the buildup of momentum in the reaction wheels because of the solar pressure on that star shade wanting to sort of tip it over. But in answer to the question, most NASA missions have not been designed to be serviceable, and once you get out to L2, it's extremely hard to do servicing of a mission out there. And in particular on cryogenic missions where you're really packaging the instruments and a lot of the hardware in many, many layers of multi-layer insulation, it's not like Hubble where you open a door and pull out the box. Everything is heavily gift wrapped, if you like, in MLI, so it's a lot harder even to get access to the instruments.
Okay, well, good. Well, Gary Matthews, so I want to thank you for, all eyes have been on you guys for putting this thing together, and I think you've done an outstanding job. We're all extremely excited at the work you've done, and with just the amazing level of accomplishment that you all have. And as you've already said, there's no time to rest, so you're moving on. I hope that as the year progresses, you might come back and tell us some more about how you're doing.
Yeah.
I'd love to come back. Thank you for inviting me today.
It was a real pleasure and an honor to talk to you about all this, and I just want to thank you.
Especially since he's like the director of the universe, so
yeah.
Seriously.
I send my grand proposals to you, director.
You know what? What I want to know is, did he bring his towel to the job interview? That's what I want.
That's true. You always need to know where your towel is.
That's right. All right. Well, Dr. Mark Clampin, thank you so much for taking time out. I know you're very busy, and thank you for showing up again on our Hangouts. And Gary Matthews, thank you also. And I will look forward to hopefully talking to you as more milestones are reached on the JWST mission. This is getting so exciting.
It is. It really is. And thank you guys so much for your time. I really appreciate it. I know you're incredibly busy, but thank you.
And we've got just, I think, a couple of minutes. I forgot to ask Scott about things like Twitter and all of that. Did I miss anything else, Scott?
We've actually touched a lot that was already brought up in Twitter. Lots of congratulations are actually being said on Twitter. So there's a well-deserved congratulations. Yes. And we're right there with you. Congratulations. This is a great milestone. We can't wait to hear more.
Yeah.
All right.
All right.
All right. Well, with that, Carol, do we have anything on tap for next week, or is it a surprise?
Another surprise.
Oh, another surprise.
Hangout surprise.
Yeah. So next week. All right, folks. All right. Well, that's it for this week's everybody, and I want to thank you all for watching. We'll be back next week, same Hubble time, same Hubble channel, and we will be talking more about science and the mission of the Hubble Space Telescope. So thank you all for watching, and as always, keep
looking up.
Thank you.
Already seeing a bunch of guys in there. So since we're streaming live on YouTube, we've enabled the YouTube live chat to where you can chat with each other. You can ask us questions and make comments. And as it's going on, I'll be perusing through there and directing any questions that are going on in your chat onto the show. So please keep on doing that. Also, while we're going through, we'll be live tweeting from @Hubble Telescope, and we'll be using the hashtag Hubble Hangout, even though this is JWST related. So I'll be looking at everything over there on Twitter. So please feel free to ask us any questions, make any comments there that you feel is really important to what's going on here, and we'll try to get them up live on the show.
Awesome. Great. So we hope you guys will have some great comments and questions for our guests today, because with me today are two people involved very heavily in the JWST mission. With me is Dr. Mark Clampin. He is now the director of the Astrophysics Division at the Goddard Space Flight Center. He used to be the observatory project scientist for JWST. Welcome, Mark. It's glad to have you back in our Hangouts.
Pleased to be back, Tony. Thank you for having me.
Cool, great. And also with me is Dr. Gary Matthews. He has the coolest job in the universe. It's one I want when he decides to move on. He is the director of track of all of the social media stuff during the Hangout. Hi, Scott. It's good to see you again.
Good to see you too, Tony. How's it going?
I'm doing great. Like I said, I am psyched. And cannot wait. Cannot wait to talk about today's stuff.
You're cheating on the Hubble huggers. So
I know. He's listening as a good.
You know, Hubble is great to hug. JWST is a little bit pokey. I don't know if I could hug it as nicely. It's also really big, so I don't know if it's
it is really
easy to hug. It's got a lot of little pokey sides on it. I'm not sure it's
But speaking of, I might have a picture later on of you and me hugging.
Yes, I saw it on Twitter.
No,
Thank you for
no,
that.
that's okay.
And not me
It's
actually.
related to JWST too, so it's even better. It all ties in.
You know what I should do next time I'm at the Institute is I should go to the lobby and actually try and hug that big scale model. That's what I should do. Okay, so we're going to get started, I have an anecdote that I want to share with you today. My anecdote is about Clyde Tombaugh, because today marks his 110th birthday. And my anecdote is, I actually met him. I got a chance to meet Clyde Tombaugh. He is the discoverer of the minor planet Pluto, but at the time he discovered it, it was
dwarf planet.
Dwarf planet, okay. Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and today I am psyched. And I'm psyched because I am going to loosen my hug on Hubble just a little bit today, and I'm going to be giving some love to its successor, the James Webb Space Telescope. And today we're going to be giving some love to that because we've got an important milestone that was reached today because NASA announced, drum roll please. Oh, thank you for doing that. The 18th and final mirror segment has been installed on the primary mirror plane for the James Webb Space Telescope, and we're going to talk about what that was like, what that process was like, and with the people who are involved both in overseeing the James Webb Space Telescope as well as those actually building it. And I'll introduce my guests here in just a minute, but before I start, let me welcome my friends, co-hosts, and colleagues, Dr. Carol Christian. She's the Hubble Space Telescope Outreach Scientist. Hi, Carol. It's good to see you again.
Hello, Tony. Good to see you, too.
Yes, I hope so. And also with me is Scott Lewis. He is the Internet Driver Extraordinaire. He keeps, yeah, well, words are important, so I should get it right. Dwarf planet, Pluto. And I met him at, you may not know this, but my very first, well, I know you don't know because I'm telling you for the first time. My very first job right out of high school was working at a place in Alamogordo, New Mexico called the Clyde Tombaugh Space
I already heard this
Theater.
story. I already heard this story.
You have, but not everybody else.
Well, that's all that matters, Tony. Carol.
So Carol's heard it. Anyway, I met him. He was a wonderful man. He was very kind, very generous, and he was very inspiring to talk to because he was, telling us all kinds of stories about his telescopes because he observed, I think he lived in Las Cruces, and he told us all about the telescopes that he used. So in honor of him and his 110th birthday, I just wanted to give him a shout out because he's an awesome person and very inspiring.
Yeah, really.
So that is my anecdote. Okay, let's get to the hangout today. But before we start, we need your interaction, folks. We need you guys to get involved. And that means we want your comments and your questions. And to tell you how you can do that is Scott Lewis.
So we've changed things up. We're following how we were last week, and last week was wonderful. So we're going to keep that going on here. And I'm
of universe exploration. That's a job.
Right. That's a good title.
What?
It's a great title.
I can imagine. Boy, I don't. That must. That's my old job, actually. I hope you. I hope you can keep up with that. So.
Well, since I own my own business, I think I'm going to change my title to something similar to that, and just go with it.
Right.
New business in order.
So, for those of you who don't know, Harris Corporation is a subcontractor for Goddard. I mean, for Northrop Grumman, and they were the ones responsible for getting the mirror assembled today, and we're going to talk to them about what was involved in that. But before I ask you my first question, Scott, can you put up that picture of what people who work at Goddard see when they come to work? This is what they see now at the Goddard Space Flight Center when they go to work. Dun, dun, dun.
Well, you could have told me that was the first one.
I should have told you to cue it up.
That would have been nice.
I should have queued it up. So he's getting it together right now.
Yeah, just a second. Let me get it.
And then while he's getting that up, I should also, another question that I would like to ask you guys